I think we will make a start. So hi everyone, and welcome. Thanks so much for joining us today for our second seminar series organised by the IGAC ICAC Early Career Scientific Steering Committee. These sessions are really sort of all about giving early career researchers a platform to share their work to the sort of global ECR atmospheric chemistry community. And it's really great to have you all here to support our two speakers today. If you would like to nominate yourself or a peer for a future seminar series, you can do. I'll put the link for the nomination form in the chat. So it'd be really great to get sort of a few speakers lined up for the next series. But as I say, today we've got two fantastic ECRs. So first up, we have Prince Junior Asilevi from Kwame Nkrumah University of Science and Technology in Ghana, and he'll be talking about NO2 meteorology and predictability over West Africa using Tropomi. And then we'll hear from Ariel Scagliotti from the National Atomic Energy Commission in Argentina, and he'll focus on uncertainties assessment in aerosol optical classification. So this is really a space for sort of, sharing our research and ideas, learning from each other, and building connections across our global community. So we really encourage you to ask questions and to join the discussions after the talk. So thanks again, everyone, for being here. Over to you, Prince.
Okay, thank you very much. Okay, hello everyone. Yeah, can you hear me?
Yep, we can hear and see your presentation.
Okay, thank you very much. Hello everyone, my name is Prince Junior, and I'm a teaching and research faculty at the University of Kwame Nkrumah University of Science and Technology, and I am in the Department of Meteorology and Climate Science. I'll be speaking this moment on NO2 meteorology and predictability for air quality management over West Africa using Tropomi. A moment, please. Okay. So I'll be speaking on NO2 meteorology and predictability for air quality management using Tropomi. So briefly, I will just take you through a background of what my work is about. The main issue of NO2 being an atmospheric pollutant and why NO2 is very important for atmospheric chemistry, and what are some of the monitoring challenges that we have in our part of the world. And then I will mention the study framework or the data set and the tools that I'm using for this work, and then share my results on the NO2 variability, the NO2 meteorology relationship, because in this work we are trying to leverage on the meteorology to see to the prediction of NO2, and then we look at the model performance as well. Okay, so like we all know, this is basic to atmospheric scientists, that NO2 is a highly reactive and it's a criteria pollutant according to the US EPA, and exposure to NO2 is irritating to respiratory systems, and so NO2 is of importance to us as atmospheric scientists. Largely, NO2 sources include mainly combustion sources, but there are also natural sources like lightning and so on and so forth. NO2 emissions is key, largely because of its contribution to ground level ozone pollution and acid rain and a host of other environmental problems related to nitric acid formation and so on and so forth. So we find it very important. In our part of the world, there is, because of increasing population, we are increasingly becoming aware of ground level NO2 pollution and the increasing effects that it has on both the human health and the ecosystem health as well. But we have major challenges because we are aware that NO2 is a problem, it's an environmental problem or a public health problem, but our major challenge is that we lack ground measurement. We lack ground level measurement, and then we don't have the facility largely, okay, to do a lot of this monitoring. Recently, there's been interest in air pollution, but you notice that a lot of the work that has been going on has centered on particulate matter, PM 2.5 and PM 10. There is very little work on gas phase pollutants. And so we try to solve this problem by trying to use satellite data from Tropomi to understand the NO2 distribution, hotspot regions, and possible predictabilities. This is important because first of all, we don't have the data. So if satellites can give us the data, and then we have meteorological measurement, because we have meteo stations within the region, then we can look at the pollutant concentration meteorology relationship, and then if we can assume that if we understand the distribution of the pollutant, we can assume that, granted that the emission sources are still as they are, then we can use the meteorology to predict. So that is it. Some studies have shown that a large source of the NO2 is coming from the traffic, from automobiles, like this study. But one major setback of this study is that it focuses on urban regions, and so you lack a regional distribution or a regional understanding. In this work, for computational reasons, I will be focusing on the southern part of West Africa, which is particularly I'll be focusing on Ghana because it's easier to get meteorological data from this region. However, it's also a region fit to describe the climatology of the area because we share similar monsoon climatology, the wet and dry climatology, and then the Sahara dust storm during the dry season. So basically, I'm using data from Tropomi. We know that Tropomi is coming from ESA, from Sentinel. However, this data has been developed and prepared by NASA HACCAST. And then I am coupling this data with this Tropomi NO2 with NASA Power. NASA Power 0.5 degree grade meteorological parameters. Plus, also we are using fire data from MODIS and some seasonality index. So basically, we use the seasonality index to understand the seasonal distribution of the NO2 over the region. And then we use some the predictive models that we have used. We have tested between the NO2 and the meteorology to find the relationship and the predictability of the NO2. We tried 5 different models: the linear regression, the ridge regression, the random regression, and then the gradient boosting, and then the extra gradient boosting regression model. So as usual, we use the 8:2 ratio concept, where we split the data into 2. So I used 2019 to 2021 data, and then to test the model, or sorry, to train the model, and then the 2022 data to test the model, to test its performance. All right. So basically, this is the annual distribution of NO2 over the sub-region, particularly focusing on the Ghana, Togo, Cote d'Ivoire, Burkina Faso area, where you have NO2 distribution. So this is directly from Tropomi. This has not been computationally changed. Okay. So you can see 2019 and then 2021, 22, and 23. You can see the distribution, the annual mean distribution of NO2. And you can see that there seem to be the highest concentration over the northern half. However, you can also see that there is a hotspot down here. And of course, that is the Greater Accra region, where that's the capital, the industrial hub of that region. So that explains why there is a hotspot. You can see that it's almost consistent throughout all the years. You can see the COVID-19 phenomenon also after 2020. You had a slightly reduced NO2 concentration over the region, which seemed to have increased again in 2022. Seasonally, you can see that the NO2 concentration is highest during the dry season. So you have NO2. So this is the dry season, which is the December, January, February period. And then you move into the March, April, May, where the rains begin. And then the rains begin to peak using, according to the Intertropical Convergence Zone pattern, where the rains peak in the June, July, August. And then the rains begin to subside in the September, October, November. You see that there's high levels of NO2 in the dry season, and then it subsides almost to zero in the peak of the wet season, and then it begins to build up again from the northern side, in the ending of the rainy season. Now, because one major source of NO2 is combustion, okay, biomass combustion. So we try to use fire to see if fire data to see if there can be a correlation between NO2 emissions and fire. And so the plot down here is the FRP, the fire count for Moody's, and you can see that there is the NO2 distribution fairly mimics the fire distribution. So just as you have the highest concentration of NO2 in the dry season, you have the highest fire count also in the dry season. Just as you have zero to low NO2 over the region, you also have you have almost no fire count in the wet season. And it's very interesting also to notice that just as the fire begins to build up in the northern region, then the NO2 also begins to build up. That's quite interesting. However, it's also important to notice that in the industrial hub, even all throughout the seasons, in the peak rainy season, where the NO2 levels are regionally subdued, the industrial hub is moderately significant. So basically, you see that the northern half of the region has a high seasonality, and then the southern half has a low seasonality. There are two reasons for the southern half. When you have, for example, you have the forest hub. There's a forest hub in the southwest, where there are completely low levels of NO2, so the seasonality is low. But in the industrial hub, in the Greater Accra area, where you have high emissions of NO2 from traffic and from industry, you can see that because it is a consistent and it is anthropogenic emissions, the distributions are fairly moderate. Okay, all throughout the year, it's almost consistent. So that makes it not a very significant seasonal phenomenon. Yeah. So meteorologically, key weather patterns that seem to drive NO2 across the region are temperature, humidity, and wind speed. So generally, when you have warmer conditions, there is expanded air, because this is a tropical region. So there's always the air expansion when you have warmer temperatures, and then the ability to accommodate more fires, okay, and then also more NO2. Wind dispersion is also very key in causing distribution of NO2. And then the key weather parameters that subdue NO2 distribution is rainfall and humidity due to the process of scavenging. So we tested model predictions from different machine learning techniques, and we noticed that generally across all the so we divide the region into 4 climate zones. We have the savanna, we have the transition zone, and then the forest zone and the coastal zone. So you notice that the different models perform fairly very well across all the climate zones, but of course some perform better than others. You notice that, for example, over the coastal region, the gradient boosting technique doesn't seem to perform too well. Generally, the linear regression model performed best over the coastal region. So you notice that even though all the models are predicting monthly mean NO2 over the region fairly well, they behave differently across different climate zones. So, for example, you can see that in the savanna region, where the climate is a bit more less sophisticated, the linear regression and the ridge regression models do quite well in predicting NO2. You also notice that in the transition region, which seem to share a transitional behavior between the savanna and the forest, you have a random forest model performing quite well with about the Pearson's correlation of 0.2, 0.87. The forest zone, which perhaps has probably the most complex ecosystem, required some more sophisticated machine learning technique. So the gradient boosting and then the extra gradient boosting models seem to have performed, seem to have shown the best performance. And then finally, with the coastal zone, you have the ridge regression also performing quite well. Of course, the linear regression also did quite well, but relatively with respect to the Pearson's correlation, the ridge regression did the best. So in conclusion, regionally, we see that there is a NO2 peak during the dry season. There is NO2 peak during the dry season, and then there is NO2 subsidence, NO2 subdued during the peak of the rainy season. Because this is due to the hydrodynamics or the scavenging effect of rains. The key drivers is biomass burning, because you can see that the fire distribution just mimics the NO2 distribution. The random forest and the extra gradient boosting technique or models better predict largely over the area, especially within the middle belt. And we have shown that machine learning techniques can be used to leverage on meteorological data to predict NO2 over the region. Thank you very much.
Thank you, Prince. That was a really great talk. Some really interesting results there and such high quality. We're always so impressed with the presentations that ECRs give. And with that, I'd like to open the virtual floor for questions. You can sort of like unmute yourself or type a question into the chat. But maybe whilst people are thinking, I can get one started. So when you were displaying the emissions from 2019 to 2023,
Yeah.
you had sort of the decrease in 2021 that you attributed to COVID. But I guess when I think about COVID, I also think about 2020 as well. And you don't see such a big decrease in 2020. And I just wondered if you had a feel for sort of why you see such a big difference between 2020 and 2021.
Okay, very good. So thank you very much for the question. So you can see from the seasonal distribution, that the peak NO2 is in the dry season. Yeah, during the December, January, February. We had a lockdown after the peak season. in 2020. Yeah, so that explains why you have some peak in the 2020, and then in 2021 you have the subsidence, and then it surges up again.
Thank you. That makes sense now. Any other questions?
Yes, I had one. Thank you, Princess. It was a very good presentation. And I was wondering about the indicators you use to evaluate the performance of the models for evaluating the impact of meteorology in NO2 concentrations.
Yeah, come again. You wanted to?
Yes, about the way you evaluated the performance of models.
Okay.
I don't know if you have ground stations, for example, or you use indicators of the models dividing the data set.
Okay, so like I mentioned earlier, we lack ground data. There's no NO2 ground data. So we are experimenting using weather data based on the NO2 weather relationship to predict NO2 from the weather, because we have ground weather data. You understand that? So here we use the weather data from NASA Power, which of course we can get from the meteorological stations here, which is not difficult. Then when we use based on the relationship, we estimate the NO2 based on the weather. Then we get an estimated NO2. So we use statistical indices to compare the estimated NO2 and then the derived NO2 from NASA. Yeah.
Thank you.
So it's not ground validation, but it's just model performance. Yeah.
Thank
you. Any more questions? Well, I have one more, if you don't mind. The models that you say for sort of like the more complex systems don't perform as well. Is this because there's like sources that we don't understand, that we're unaware of, or we're not aware of their source strength, or is it more sort of like a process level that either it's difficult for these models to like replicate, or again, it's just a lot of like maybe processes and chemical transformation that we're unaware?
Yeah, I think so. I think there are conglomerate reasons. For example, don't also forget that the NO2 data we are using is not a ground level data; it's a tropospheric column data, and then the meteorological data is ground level data. So these are some inconsistencies in relating to even the data marrying the two data sets. In connection, on the flip side of the coin, there could also be, for example, the chemistry, okay, because nitrogen dioxide is short-lived in the atmosphere. So, and then also because it is short-lived, we could see from the distribution that it is also highly variable across the region. And then also there are different land use, land cover impacts. So these are a number of forces interplaying to influence the distribution of the NO2. So the relationship between NO2 and the meteorology is rather complex, depending on the climate zone that you find yourself. Yeah.
Thank you. And I think Terence, would you like to unmute yourself? You've got a question.
Oh, okay. Thank you very much. I just have a quick question for you, Prince. Have you considered, I mean, because we know that in most of the cases, the emissions, as they will contribute to the concentrations as a result of power stations or some of anthropogenic activities. I mean, have you ever thought of, bringing that in place for this kind of beautiful study that you're presenting?
Yeah, so like I mentioned, you can see from this particular slide that a major contributor of the NO2 during the dry season is coming from biomass burning, which is largely anthropogenic.
Come again?
Yeah, so like you can see from this particular slide,
Yeah.
okay, you can see that the highest concentration of NO2 is in the dry season. And it mimics biomass burning, which is recorded as fire from Modis. And this biomass burning is largely anthropogenic. It's due to maybe farming practices or some dry season burning or so on and so forth. This is largely anthropogenic. So I think from the results of this work that the major source of NO2 in the atmosphere over the region is largely anthropogenic, especially because of the seasonal behavior.
Okay. No.
Yeah.
I think we've just got time for one more question, and there's one in the chat. So from Kern, great talk, Prince. Given the complexity of this relationship between meteorology and NO2, what are your thoughts on using a model to obtain ground level NO2 from Tropomi and then doing the predictions?
Come again with the question, please.
It's in the chat if that's easier.
Okay, let me read the chat. Okay. Yeah. So he's saying that given the complexity of this relationship between meteorology and NO2, what are your thoughts on using, I can see it clearly, on using what?
A model to
using a model to obtain ground level NO2 from Tropomi. Okay, and then doing the prediction. Okay, very good. So that is a great question. I've seen some papers where they have used a conversion factor. Now, this will work if you have ground level data. This will work if you have ground level data. So you can use the ground level data to statistically bias correct the Tropomi data. Okay, but that is fantastic. If you have ground level data, then you can do that. But because we don't have ground level data, we are using ground level weather data to predict the tropospheric column NO2 data. I don't know if I have very well answered your question.
That's okay. Maybe whilst Ariel is setting up their presentation, David, you can quickly ask yours, and then any questions you can just sort of put in the chat, and maybe Prince would kindly reply.
I think there's another question in the chat. It says that can I get the code to do the study or repeat it in some other location? Yes, of course you can. I can share it by email.
Wonderful. That was an easy one. And now we can sort of load up the presentation for our next speaker. Thank you, Prince, again for that great talk.
Thank you very much.
Any more questions for Prince? If you put it in the chat, then maybe Prince can type out some replies if there are a couple more questions. But we'll move on to our next speaker.
Right. I guess I can stop sharing my screen, right?
Yep, that'd be great. And Ariel, hopefully you can share yours.
Yeah, can you see my screen?
Yes.
Okay, great. Okay, thank you very much for this initiative, this opportunity to share our work. Very happy to be here. And I'm going to talk about aerosoloptica classification, more specifically uncertainties assessment. I'm going to then make a brief overview. Sorry if some of you already noticed, but it's going to be brief. And if you have any questions, I'm happy to answer them after the talk. The main topic here is to monitoring the atmosphere using sunlight. We use some photometers in the ground pointing to the sun. Then we can measure the attenuation of solar radiation in different wavelengths because of different factors in the atmosphere, like the air itself, water vapor, ozone, other gases, aerosols, and so on. Through the number below, we can separate the contribution of each of these factors in the solar radiation attenuation. And for the specifically aerosol studies, we are going to focus on AOD, which can be seen there in the equation. Is the aerosol optical depth, which is the extinction of solar radiation for the presence of aerosols. And we have different networks and different instruments working in different places of the world, but the golden standard maybe is IRONET, the Aerosol Robotic Network from NASA. They have many stations around the world with a good coverage and very thorough protocols of calibration of instruments. And they offer different kinds of products. We can divide them in three different factors. For example, direct solar radiation, which is the aerosol optical depth, which I mentioned before, the Armstrong exponent, which is the spectral dependency of AOD in a logarithmic space. It's more like a qualitative measure of particle sizes. Then we have the spectral deconvolution algorithm, which allow us to divide between fine and coarse mode fraction of particles. The fine mode fraction there is the most used product. Then we have the inversion code, which has many different products. The more used maybe are single scattering albedo, complex index of refraction, and so on. I put there in this slide 6 different aerosol classification schemes. We can use these products to classify aerosols using mainly their absorption properties and their size distribution. And these 6 schemes are ones of the most used in literature, but there are more, of course, and different studies determined different thresholds in these two-dimensional schemes to classify aerosols. For example, in the first one, Cuneo et al. 2022, we have 4 different regions, which means to classify aerosols like maritime biomass burning mixed aerosols. Is the extinction Armstrong exponent versus AOD method, which is one of the most used methods in the world. The problem with this kind of schemes is that they are determined in some part of the world, and that doesn't mean that they are going to work well in other parts. But in many regions, we don't have a thresholds determined in that place exactly, so we have to use from other parts. This is another problem, which is the associated error, the uncertainties in classifying aerosols with this method. All these products has an uncertainty. AOD, for example, for certain wavelengths has 0.01 units of AOD of uncertainty. And I asked, what are the uncertainties in classifying aerosols with this method? Because that is something I didn't see in literature, and I believe it's very important. And also, does these uncertainties depend on the classification scheme, the type of aerosols I'm classifying, and if there is, there are different discernible patterns in this classification that enable us to minimize these uncertainties. If we look at the literature, we are going to find that inversion products are preferred because they have low uncertainties. But the problem is that in many regions of the world, they have low availability. For example, we made a study in South America using 30 different IRONET sites with 5 years of data. And in average, we have almost a 50% of availability for AOD and fine mode fraction, but in most cases, a 2% of availability for inversion products. And that's a problem because Many authors recommend to use a 0.4 units of ALD thresholds. That means if we have a daily average of ALD less than 0.4 units, then we discard that data. That assures us to have lower certainties, but the problem is that we are going to have low representativity of the aerosol situation in that particular site. And in many regions of the world, we are going to have low inversion products availability because if we have low ALD values, then we are going to have low inversion products data. So I wanted to know about the uncertainties of different classification schemes because in some parts of the world, we don't have another alternative that use direct solar radiation products. So we retrieve different primary variables and calculated derived variables like extinction electron exponent, the absorption electron exponent, the aerosol relative optical depth, which is the relative value of ALD in two different wavelengths. Then we applied different classification schemes, the most used classification schemes in literature, and we used some methods to error propagation. We took the uncertainties of the primary variables and propagated to the classification schemes. And for the derived variables, we used partial derivatives to do so. And the outcome here is the misclassification rates, which is like a percentage of possible misclassified points using a particular scheme. For example, in the case of the electron exponent, which is a derived variable, like I said before, is the spectral dependency of ALD in different wavelengths. And we use partial derivatives to propagate the uncertainties of ALD in different wavelengths to the calculation of the electron exponent. Then we can see down there in the plot, with that we calculated error bars for each point in the scheme. And if a point can fall in two or more different aerosol types, then we counted like a possible misclassified point. That is the case, for example, of those 2 points that are highlighted in the plot. They can belong to average continental type of aerosols or to mixed aerosols. And normally we classify them as average continental because they are inside that box, but the uncertainties tell us that they can fall in another type of aerosol. So that's a possible error in the classification. We have here two specific examples. We use, for example, Alta Floresta and Solar Village, which are two of the most used sites, Ironet sites in literature because they have long-term data and they have low gaps in the data sets. And we applied several different classification schemes in these two sites and for 5 years of data. And we find out that the best and the worst scheme with the higher and the lower uncertainties are different for each site. For example, for Alta Floresta, we find that the aerosol relative optical depth versus ALD is the best scheme with almost 40% of uncertainties. But if we use the real refractive index versus extinction electron exponent scheme, we are going to have more than 60% of uncertainties. So the inversion products are not always the best answer. And if we analyze Solar Village, we are going to find that Feynman fraction is the best scheme with a 12% of uncertainties, and the single scattering albedo versus extinction electron exponent have almost a 60% of uncertainty. So Again, the inversion products here are not the best option. So we find out also that the uncertainties depends on geographic location, biome, climate, type of aerosol. Also that all methods perform poorly with low ALD values because all methods are going to have high uncertainties in those cases. So it's very important to understand these uncertainties and to select the best option of a scheme. Normally in literature, we use the most used scheme for other studies with great results, but that doesn't mean that they are going to have the same results with our data. For example, if we have low ALD values, then we want to use low complexity scheme. That means a very complex scheme with many thresholds and a lot of type of aerosols to classify are going to have great difficulties, high uncertainties. So in those cases, we want to use a very simple scheme. And the correlation with type of aerosol, location, biome, climate are very strong. And I think this can help researchers to select the most suitable method for their studies. And we continue working on replicating this methodology with other sites and data sources. So far we use IronNet, but we want to use other data sources. And we are developing an open source package for aerosol optical classification. So the user can input the data and the outcome is the uncertainties of using different aerosol classification schemes with that data. And of course, we want also to advance in creating new classification schemes. For example, in Buenos Aires, we have enough data to create new thresholds for that particular site, but we are still using thresholds and schemes determined in other parts of the world. And the next step will be to use machine learning also to optimize classification. We want to combine different classification schemes to create a model with machine learning. We believe that would be very interesting and could have good results. Well, if you want to learn more about this, I leave you there the last paper we published in South America. And that's it. Thank you very much. Down there is my email if you want to write me, and I will be happy to answer any question you would have. Thank you.
Thank you very much. Again, another really great talk. I see we've already got one question from Max in the chat. So he's saying, naive question, does the wavelength give information about the altitude where the aerosol's plume is located, or do you need auxiliary measurements such as LiDAR? It's also in the chat.
Yes, we will need auxiliary information for have that results, because, for example, we have LiDAR instruments in different parts of the world. Also, satellite LiDARs are LiDARs in the ground and in satellites, and we can use that information to understand the vertical distribution of aerosols. That is something that we still didn't do, but we are interested in adding in our research.
Thank you. Any other questions? I have one. So I'm very much like I'm an observational person. But as well as sort of for your method being limited by like available measurements, are you limited, because this is like for running your model, are you limited by like computational power that you have access to? Like, do you need access to like supercomputers for this, or is this sort of a model that sort of any sort of
Yeah.
research?
No, for the development of the package we are made, we don't need too much computational power, but for the machine learning techniques, we are using a lot of data. So there we are using a cluster to perform the computation.
Thank you. Any more questions? They can also be typed in the chat if you prefer, and I will read them out. Also, yeah, me and Max both measurement people. Have you thought of vertical sampling method to validate the model? Something like drones or balloon sampling?
Yeah, that's a very interesting question. We thought about that. We start searching for different options. So we are working with low-cost sensors for measuring particulate matter, and we did some tests with a balloon for measuring, but they have a lot of problems like the wind and the uncertainties from the low-cost sensors. So it's still, we are still working on that.
That sounds like a fun campaign.
Yeah.
How far back do these sort of like, can you sort of look further back in like history with your model and sort of like capture sort of how aerosol optical depth is like changing over time in your region?
Yes, we work on that. We didn't put focus on that, but there are different studies. For example, it was very interesting the works during the pandemic, the difference prior, during, and after the pandemic, the changes, and also a very interesting outcome of those kind of studies. We made some of those in Buenos Aires, and depending on the meteorology, the conditions, we can have an inversion relationship with particulate matter, and that's because the vertical distribution according to the boundary layer characteristics, and that was a very interesting outcome. And during time, we particularly don't have many results about that, but we study some of them.
Thank you. We're starting to get sort of close to the end of the seminar. So if you have any questions, any further questions, you can just type them in the chat whilst we're wrapping up. Or please feel free to get in touch with our speakers via their email. So again, just want to thank you all for joining us. And again, to remind yourselves to nominate yourself or a peer for a future seminar series. We hope you've really enjoyed today's talks. It's always nice to see there's some other things from what people are up to. And also just sort of from the committee, we're currently working towards an ECR perspective piece paper for IGAC's 35th anniversary special issue, which will be published in Elementa later this year. So we'd be very grateful if you could fill out our survey as well as share it amongst your network. So I will put the links in the chat. We have one in English and also one in Chinese. So I think that sort of brings us to the end of today's seminar. But I'd just like to thank again both our speakers for some really great talks. And to Prince and Ariel, well, I'll send you a certificate of sort of like participation that you can sort of keep for your records. We know some universities like that you have sort of this official documentation. So we'll get that out.
All right.
But thank you both so much for giving up your time.
Yeah, that'd be great. I wanted to ask you about that earlier.
Okay. I haven't seen it yet. But yeah, we'll get that to you. Yeah, thank you both so much again. They were really great talks. I think ECRs do a better job than senior scientists sometimes.
Thank you very much for the invite.
Yeah, thank you very much.
Thank you.
Hope
Thank
to
you
see
very much.
at future IGAC events. Bye. Bye.